Okay, the final video here, the one on titration. And I'm going to tie it together with the buffers because this is what's going to make buffers make a little bit more sense. Right, titrations. I'm going to approach it from the acid point of view. Oh, I should say the weak acid point of view. The weak base, you're going to have to go through yourself. But it's the opposite of this. Now, in a weak acid titration, we're going to take our, oops, let me get my pen here. We're going to take our weak acid, and notice it's written unionized. It's weak acids stick together. They hardly ionize at all. Now, you don't worry about what's ionized on this already. You take the weak acid just exactly as it is. Here it is on our chart. We've got our weak acid. Let me get my little highlighter going. We've got our weak acid right here. It is all HA. And we're starting at a pH of around 3 because it is a weak acid. Now, if it's down to 1, it'd be a strong acid, most likely. And right here, you could end up finding the hydrogen ion concentration, Ka times the concentration of the acid. This part, this equation applies at the very, very start of the titration. When we just have our weak acid in a flask and we're going to dump some base into it. So that's what we're going to do next. We're now going to take and add hydroxide. Hydroxide from a strong base. It is a strong base. And it's going to, as soon as it sees this acid, it's going to react with it 100% and make some water, which we don't care about, and make, very, very critically, some conjugate base. So right here, we are starting to wipe out some of our acid. In effect, we're getting rid of that acid. Now you'll notice I made the HA a little bit smaller because some of it has been reacted and we're making a little bit of A-. The pH is going to increase because we're losing some of our acid that makes H+. And then we're sort of leveling off a bit because we're starting to make a buffer. And this is the other important idea. You can make a buffer by starting off with just weak acid, dumping some hydroxide in, a strong base. That strong base is going to disappear because it's reacted with the HA, but we still have a lot of HA left, and we're making some A-. So all of a sudden now you have HA acid, its conjugate base. In fact, this is one of the best ways to make a buffer because you don't have to go looking on the shelves. Where's the conjugate base that's going to match my acid? You're going to be making it right then and there. Now that's going to keep on happening. As we drop in more and more hydroxide, as more and more of this hydroxide comes in, we're going to be getting to a situation, now let me switch to the green, where the amount of acid left is going to equal the amount of conjugate base you made. Now that, I hope, rings a bell to you in terms of buffers. When you have an equal amount of acid and the conjugate base. I'm going to return to this later because we're going to keep on doing this. We're going to keep on adding. This is what the titration is all about. We're wiping out that acid. The idea of the titration is, let's see how much it takes to wipe out this acid. Now our acid concentration is so low that almost none of it is left. But we have lots of conjugate base. So now our pH is going to start skyrocketing until we wipe out all of the acid. And that's the end of the titration. That should be the end of the titration. The acid's used up. This is where our equation, where the concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. Because we've wiped out, we put in equal moles of acid and equal moles of base. We had the same of both of these, the equimolar point. And all we have right now is A minus, which is the conjugate base. And of course, if we just have A minus, then this original weak base equation comes into play. And you can end up using that. Now, let's go back. We found out how much it took to wipe out that acid so we could figure out its concentration. But once you know this amount, let's say this was 22 mLs. It took 22 mLs of base to wipe out the acid. At half that point, at 11 mLs, the HA equaled A minus. The acid and its conjugate base buffer were in the ideal buffer range, where the pH equals the pKa. In fact, this is a great way of finding the pKa of an acid. Titrate it with a base, go all the way to the end, and figure out what the pH was halfway through that. Now, if we keep adding, if we still have a lot more hydroxide in that burette, and we keep adding, that, let me switch to a different color. pH is going to shoot up because we've got nothing but hydroxide ion. After this point, you're adding just base. Forget about the acid. Forget about the conjugate base. You're just adding strong base. This is just hydroxide stuff. So this last part of the titration is sort of, why even bothering? Because you're just adding hydroxide. So it looks pretty. I sort of like the S look here. But really, the important part of any titration is this part, where you're starting to get rid of your acid, getting rid of your acid, got rid of half your acid, and you have a perfect buffer where the pH is equal to pKa until finally you get the equimolar, where all you've got is base. So look, here we are starting with acid. Here we are with its weak conjugate base and the middle point. So that's it. Now, you're going to have to think this over in terms of doing it the other way around, where we have a weak base and we titrate a weak base with a strong acid. But still, the pH is going to be equal to of our titration, because we keep track of a pH. Even when we're dealing with in fact, let me do a little drawing. Next page. Here, if we end up having we're starting off with a weak base, here maybe probably at 11, and we add to that a strong acid.